Okay. Good morning. I'm Amir Yasir from Aligarh Muslim University. Uh, I have a presentation on design of a Tfet based temperature invariant LDO voltage regulator. My paper ID is 52. These are the overview of my presentation. First, I introduce the topic, then some basic concepts of Tfet, that is tunnel field effect transistors, then error amplifier, which is basically a two-stage Tfet based op amp, then low dropout voltage, basics of some low dropout voltage, then simulation results, uh, then summary, and then references. A 20 nanometer Tfet based temperature invariant low dropout voltage regulator is presented in this paper. Comparative analysis is done with 32 nanometer CMOS based LDO regulator. LDO regulator is implemented using an error amplifier, uh, which is a Tfet based two stage ramp. Our amplifier has a high open loop DC gain of 66.8 dB and phase margin of 60.9 degrees. Gain bandwidth product of the error amplifier is 1.44 GHz, 3 dB frequency of 708.12 kHz, and gain margin of 18.7 dB for load capacitance of 100 femtofarad and compensation capacitance of 25 femtofarad. The compensation capacitance must be greater than 0.22 times load capacitance to achieve more than a 60 degree of phase margin. Temperature variation analysis shows that only 500 microvolts of change in the output voltage occurs for minus 50 degrees centigrade to 100 degrees centigrade temperature variation. 400 microvolt of change occurs in the output voltage for load current variation from 0 to 50 milliamperes. Designed LDO voltage regulator working with a reference voltage of 0.72 volts offers a PSR, or you can say ripple rejection of minus 39.6 dB for frequency up to 210 kilohertz. Designed different based LDO voltage regulators consumes only 113.86 microwatts of power. These are the figures for a Verilog A model schematic as well as the cross section of the N channel Tfet. It has a current source of GMVGS, and the CGS and CGD provides capacitance specs. It has the three terminals like MOSFET, gate, source, and drain, and the gate is the controlling terminal. A 20 nanometer planar indium arsenide double gate Tfet model is used. Current conduction in Tfet is different from that of MOSFET as it uses band-to-band tunneling. Tfet is a promising technology for low power and low voltage application. Tfet offers a minimal subthreshold slope owing to its current conduction mechanism, that is band-to-band tunneling, attributed to the steep subthreshold slope of Tfet. The transconductance generation efficiency, that is GM by ID, of Tfet is higher than MOSFET in the subthreshold region. Thus, Tfet offers a low power solution for low speed applications. These are the IDVGS characteristics for CMOS as well as Tfet, uh, with a temperature variation of minus 25 degrees centigrade to 150 degrees centigrade. These IDVGS characteristics show that Tfet demonstrates the temperature variation has almost no impact in the bias region used in our work. This is the error amplifier, which is basically a two-stage Tfet based op amp. It has a bias circuit. This is a bias circuit consisting of this transistors. Uh, this is an input differential amplifier. This is current mirror load. This is output gain stage, and this is the load capacitance. For better performance of LDO regulator, the EA must have, or the error amplifier must have high gain and proper phase margin. These are the characteristics which we have calculated. for the error amplifier. A 20 nanometer Tfet model is used. Single supply of plus zero point 0.9 volts is used. 100 femtofarad of capacitive load, and the combination capacitance is of 25 femtofarads. Gain bandwidth product is achieved is 1.44 gigahertz. Similarly, CDB frequency of 708.1 kilohertz, phase margin of 60.9 degrees, gain margin of 18.7 dB, and open loop DC gain of 66.8 dB is achieved. This is the block diagram for low dropout voltage used in our work. It has uh, error amplifier using two-stage op amp, power transistor, and a feedback uh, network consisting of RF1 and RF2. It has the power transistor has higher amplifier ratios because it has to regulate high current. Otherwise, LDO wouldn't work uh, in good condition. These are the simulation results. These are the AC response of error amplifier, DC gain, phase margin, and gain bandwidth for Tfet based error amplifier are 66.8 dB, 60.9 degrees, and 1.44 gigahertz. And for CMOS based error amplifier, these characteristics are 55.54 dB, 61.97 degrees, and 221.31 megahertz respectively. Here we can see that all the other except phase margin are much better in Tibet case, while the phase margin is a bit similar in the same in both the cases. For Tfet based error amplifier, only 3.71 dB of variation in the DC gain occurs with the temperature variation, while for CMOS based it is 4.53 dB of variation. These are the dropout voltage characteristics of LDO. Dropout voltage is the differential voltage between input and output of the LDO regulator, after which LDO regulator is not able to regulate the output voltage for further decrease of the input voltage. The output voltage for TFET based LDO regulator remains constant at 0.79 volts for an input voltage range of 0.82 volts to 2 volts. Therefore, its dropout voltage is 30 millivolts only. The output voltage for TFET based LDO regulator remains 0.79 to 1 volts for temperature variation of minus 50 degrees centigrade to 100 degrees centigrade. The output voltage, on the other hand, for a CMOS based LDO regulator remains constant at 0.79 volts for an input voltage range of 1 volt to 2 volt. Therefore, its dropout voltage is 210 millivolts. Output voltage for CMOS based LDO regulator varies from 0.7934 volts to 0.7937 volts for the same temperature variation. These are the plots for DC line regulation. Line regulation of the LDO determines the variation in the output voltage with the varying input voltage. This can be considered for VDD or supply voltage variations. For CMOS based LDO regulator, the variation in the output voltage is 15.5 millivolts, while for TFET based LDO regulator, the variation is only 1.6 millivolts. For CMOS based LDO, the output voltage variation is 12.7 millivolts at minus 50 degrees centigrade, while 16.2 millivolts at 100 degrees centigrade. For the TFET based LDO, output voltage variation is 1.6 millivolts at minus 50 degrees centigrade, while 1.7 millivolts at 100 degrees centigrade only. These are the plots for DC load regulation. DC load regulation determines the variation in the output voltage as the load current is varied from minimum to maximum value. The variation in the output voltage is 900 microvolts for CMOS based LDO regulator, while the variation is 400 microvolts for TFET based LDO regulator. The variation is 300 microvolts at minus 50 degrees centigrade and 15.7 millivolts at 100 degrees centigrade for CMOS based LDO regulator, while 200 microvolts at minus 50 degrees centigrade and 500 microvolts at 100 degrees centigrade for Tfet based LDO regulator. These are the plots for PSR or ripple rejection. PSR of LDO regulator, also known as ripple rejection, determines the fluctuation in the output voltage caused by the input voltage variation. The PSRR is an AC response, and the value of PSRR is minus 24.66 dBs up to 3.162 kilohertz for CMOS, while the same is minus 39.6 up to 210 kilohertz for Tfet based LDO. The impact of temperature variation is minus 26.37 to minus 24.8 dBs for CMOS based LDO regulator, while it is minus 39.73 to minus 39.02 dBs for Tfet based LDO regulator. Here we can see each and every aspect is very low variation temperature in case of Tibet PSRT. These are the transient line regulation. Transient response provides the maximum variation in the output voltage for a step input voltage or a step load current. Here delta V in is 1.15 volts and delta V out is 8.9 millivolts, resulting in line regulation of 7.739 millivolts for Tfet LDO. The line regulation at minus 50 degrees centigrade is 1.391 millivolts per volts and 8 millivolts per volts at 100 degrees centigrade. The line regulation ability of CMOS based LDO is 15.565 millivolts per volts. The line regulation at minus 50 degrees centigrade is 42.435 millivolts per volts and 85.739 millivolts per volt at 100 degrees centigrade. These are the plots for transient load regulation. Transient load regulation is measured using a pulse load current varying from 0 milliamperes to 50 milliamperes. Here, delta I load is 50 milliamperes and delta V out is 22.6 millivolts, resulting in load regulation of 0.452 millivolts per milliampere for CMOS based LDO regulator. The load regulation at minus 50 degrees centigrade is 0.308 millivolts per milliampere and 1.008 millivolts per ampere at 100 degree centigrade. The load regulation for Tfet based LDO is 0.01 millivolts per milliampere and it is fixed for all the temperature variations. This is the summary for CMOS as well as Tfet based regulators at load capacitance of 100 femtofarad. Here we have two columns, one of CMOS as well as second of Tfet, and both the columns are divided in three columns: no temperature variation, minus 50 degree temperature variation, and 100 degrees centigrade. Okay, and this is the table which is comparing the performance with the recently reported LDO simulation units. Okay, here we can see almost all the uh, parameters are much better in Tfet based LDO when compared with reported LDOs, except the line regulation. This is the summary. Tfet based LDO voltage regulator is designed and compared with its CMOS implementation. The stability of the system is shown for considerable variation of load current, that is 0 to 50 milliamperes, and temperature variation of minus 50 degrees centigrade to 100 degrees centigrade. Only 500 microvolts of change in the input voltage for temperature variation, and only 400 microvolt of change occurs in the output voltage for a load current variation. Design circuits show good stability for different types of variations. PSRR of LTO is minus 39.6 up to 210 kilohertz. Power consumed by the LDO is only 113.86 microwatts. Tfet based LDO provides better results in all aspects except current regulation as compared to other recently reported CMOS based LDO regulators, because Tfet's on current is lower when compared with CMOS. These are the references, some of the references from the paper. Thank you.